Hello, I'm Changjiang. Today I will present our work RIAV-MVS, a learning-based method for multi-view stereo. Given multiple input images, including a reference and several source frames, our method is to estimate the depth map of the reference image. Our core idea is a learning to optimize method that iteratively indexes a plane sweeping cost volume and regresses the depth map by a convolutional GRU. To solve several concerns of existing MVS methods on feature extraction, cost volume construction and optimization, and depth estimation, our method is proposed with three contributions, including an asymmetric cost volume by a transformer block, a residual pose net to correct the relative poses, and a new paradigm to predict the depth by learning to recurrently index cost volume via GRUs. Let's have a look at again the pipeline of the existing CNN-based MVS methods. They use a Siamese convolutional encoder for feature learning, which is symmetrically applied to each frame. In addition, the CNN-based convolutional encoder does not leverage enough global contexts due to the limited receptor field. Next, given those features, a plane sweeping cost volume is constructed by matching the reference feature with possible counterparts in the source images along the epipolar line. Those possible candidates along the epipolar line are actually sampled according to the relative pose and the predefined depth hypothesis planes. It assumes the relative pose is accurate, which is not often the case, since the pose is usually obtained by various line and often contains noise. Third, the cost volume is further processed by a UNet-style 3D convolutional encoder-decoder, and a depth map of the reference frame is predicted by soft argument. The 3D CNNs are memory-consuming, and the soft argument regressor is not robust to multi-model distributions. Considering those concerns, we propose our method with the following improvements. First, we propose to break the symmetry of the Siamese network by introducing a transformer block to the reference frame. Second, we propose to incorporate a residual network to correct the relative pose. Third, as the most important contribution, we propose a new paradigm to predict the depth by learning to recurrently index the plane sweeping cost volume via GRUs. We provide more background information by comparing our method with two existing works, RAPT and RIAV-MVS. We borrowed ideas from RAPT for learning to optimize via GRU. Comparing figure A and B, RAPT performs lookup on correlation volumes for optical flow. There are no multi-view geometry constraints when generating the all-pair correlation volume. Instead, our method is proposed for multi-view depth estimation by constructing a plane sweeping cost volume that explicitly encodes the epipolar geometry. What's more, as shown in Figure E, we propose index fields as a new design. As another baseline, RIAV-MVS predicts the depth and reconstructs a new plane sweeping cost volume using the updated depth hypothesis. Instead, as shown in Figure E, our learns to index the cost volume by approaching the correct depth planes per pixel via the proposed index fields. The index fields are changed by predicting a residual update .phi to retrieve better matched cost values for the next iteration. Then a depth map is estimated by sampling depth planes using the index fields. Now let's talk about the architecture. Our network consists of feature extraction block, plane sweeping cost volume construction, GRU-based iterative optimization, including the recurrent estimates of the residual index fields, and the depth estimation by sampling the depth hypothesis. Also, a residual pose net is proposed to rectify the camera pose for updated homographic warping to construct a new cost volume, followed by the remaining iterations of GRUs. Specifically, for the feature module, the reference image and the source image are fed into the CNN feature net (FNet) for the local matching feature extraction. Besides the local features, a transformer layer is applied to the local feature of the reference image to construct an aggregated one. And next, we use the aggregated features of the reference image and the local matching features of source images to build a plane sweeping cost volume. Another network, CNET, is applied to the reference image for context feature learning, which is later used to get the GRU. The GRU-based optimization estimates a sequence of index fields from an initial starting point phi 0, which is obtained by applying soft argument to the cost volume. It is used to retrieve the cost volume. Then the index fields, the retrieved cost feature, and the context features are concatenated together with a hidden state are fed into the GRU layers to output a residual index field and a new hidden state. The updated index field is used for next iteration and so on. The last step is the depth estimation. Given the index fields phi t, the depth map is then estimated by sampling the depth hypothesis planes via linear interpolation. When constructing the cost volume, we use 64 depth hypothesis planes, denoted as B0 here. If we directly use the upsampled index fields to directly sample the planes, we see discontinuities in the predicted depth map. To mitigate this issue, we propose to use more densely sampled depth planes. For example, we sample 256 depth hypotheses for depth plane sampling using the upsampled index fields. Then, given the new depth planes and a mask, the final depth is formulated as the weighted summation within a neighbor of the predicted index. The loss is accumulated between the ground truth steps and the depth estimated by each iteration. We propose a residual pose net to rectify the camera poses. Specifically, given the estimated out-ground truth steps, the reference image, and the warped source image, using existing relative pose are concatenated and fed into a pre-trained ResNet 18 backbone, and it outputs a residual rotation matrix which is used to rectify the existing pose. Then we leverage the updated pose to calculate a more accurate cost volume, followed by the remaining iterations of the GRU. The photometric loss is applied here to supervise the residual pose network. The total loss is then defined as the sum of the photometric loss and the depth loss. Let's see the experiment results on ScanNet test sites. Here, our method is compared with several state-of-the-art methods for depth estimation. Ours achieves better performance. We also ablate the proposed residual pose module and the asymmetric employment of the self-attention layer. Each of them can bring improvement. The asymmetric employment of the self-attention is better than the symmetric one, as shown in the left figure, and also our attention module can boost the MVS backbone. Qualitative results on the test set of the ScanNet and the DTU are shown below. Our methods outperform the baseline on thin structures, small objects, and boundaries. We provide more results on depth estimation and 3D point cloud reconstruction on ScanNet. To sum up, we have proposed the RIAV-MVS, a novel learning-based MVS method. It utilizes a convolutional GRU to iteratively optimize the index fields, which are used to access the cost volume and regress the depth. The cost volume is further improved through the application of a transformer block to the reference image and a residual pose network to correct the relative poses. Please check out our poster and the project page. The code will be available soon. Thanks.